All right, here we go. Unit 4, Day 9, Basic Radical Equations. Radical, remember, just means any of these roots. So what we would call a normal square root, or any additional number of roots like a cube root or a fourth root. These are all radical expressions. And remember, what they mean is, the square root of 16 just means what number squared, what number times itself is 16, you would get 4. The cube root of, say, 8 means what number times itself, and then times itself for 3 of them total, right? That's where the 3 comes from, would give us 8. That would be 2, since 2 times 2 times 2 is 8. What if we did like the fourth root of 81? So what number times itself 4 times is 81? 3 times 3 times 3 is 27, times one more 3 is 81. That would be 3. So what we're going to be doing is we're going to be solving equations where these radicals are inside of the root. And I'm just going to show you, we're just going to do 2 basic examples today. The first one is, a normal one where you have one solution. And so we're trying to find out where the square root of 4x plus 25 then minus 6 equals 1 is true. So again, the idea here is to figure out what value of x makes the left-hand side of the equation equal to the right-hand side. And if you only have one radical term, so just that square root of 4x plus 25, the idea is you isolate the radical, so you get the radical by itself. That leaves us with the square root of 4x plus 25, which is equal to 7. And the inverse operation here, just like adding 6 was the opposite of subtracting 6, we are going to square both sides. And you are allowed to do that because you're doing the same thing to both sides of the equation, so it's not going to change the result. What that leaves us with is 4x plus 25, right? The square and the square root, they undo each other. They are inverses. They are opposites, equals 49. And so now we just have a normal, multi-step algebra equation to solve here. We take 25 away from both sides. What we would wind up with is 4x is equal to 24, and dividing by 4, we get x is equal to 6. And just to check that and to remind us, right, if you're stuck or you need help figuring something out, remember, we could just graph these. We could graph the left-hand side of the equation, the square root of 4x plus 25 minus 6, and we could graph y equals 1. Here are these two expressions. The red one is the square root of 4x plus 25 minus 6, right? Notice that it's been shifted down 6 spaces. It's been moved to the left. All of these things that we would normally expect, and then it's got the square root form. And what we can see here is that when x is 6, both of these equations are 1. So we could plug back in here, right? We could check by plugging this 6 back in. 4 times 6 is 24, plus 25 is 49, the square root of 49 is 7, minus 6 is 1. And we're going to see in a second why it's really important that you always check to make sure that these are true. Because sometimes you're going to get 2 solutions, but they won't always be true. So first, here's an example of where there are 2 solutions. So you can see how it happens. If you zoom in here, right, there are actually going to be 2 places where the left-hand and right-hand sides of this equation are equal to each other. And we should expect our answers to be -3 and -5. And the reason this happens is that when you square both sides of this equation, on the left-hand side, you get rid of the radical because it undoes square rooting. But on the right-hand side, you have to remember that x plus 8 squared means x plus 8 times x plus 8. And we have to do all of that out to get x squared plus, in the middle, you're going to have 8x plus 8x. When you do this all out, we're going to have x squared plus 8x plus 8x plus 64. So we have x squared plus 16x plus 64, remember, this is an algebra 2 style equation solve. We can never combine all of the x's and x squareds. So I'm going to move everything over to the right so that I can set this equal to 0 and use the zero product property. So I take 8x away from both sides and I take 49 away from both sides. What that leaves us with is nothing on the left. 0 is equal to x squared plus 8x. 64 minus 49 is going to be plus 25, no, 15, plus 15, plus 15. And so what we'd have here, the reason we do this, remember, is that we can now factor, this is x plus 3 times x minus 3. And so the reason we factor is we can now see there are two zeros, either x equals negative 3 or x equals, this should be x plus 3, I don't know why I wrote that, x plus 3 times x plus 5, or x equals negative 5, because those would be the two values that would cause our expression to be true. And the whole point of algebra is, if you're doing inverse operations, what makes this last equation true also makes the second to last true, also makes the third to last true, also makes the original true. That's the beauty of algebra, is that we're not changing anything, we're just rewriting it in different forms that help us see what makes it true. The answers there, negative 3 and negative 5. And we would check that by plugging these in. And so you would need to take these two numbers, this is really important here, and you would need to plug them back in. And so we would check, let's check 3, or check negative 3. We would have the square root of 8 times negative 3 plus 49 equals negative 3 plus 8. And so what we'd have here, the square root of negative 24 plus 49 is equal to 5. Yeah, that's true. The square root of 25 is equal to 5. So that one checks out. Let's also check negative 5. What we'd have there is 8 times negative 5 plus 49 is equal to negative 5 plus 8. We do that out, we get the square root of 9 is equal to 3, which also checks out. We do have to check these ones. The reason is you can sometimes get false solutions. And the reason you get false solutions has to do with this right here. It is a common problem in algebra. We kind of hide this for a little bit and then we have to go back and review it. If you square something that is a square root, you lose the information about what the sign of that thing was. You lose that information because if you take a negative and square it, it's positive. If you take a positive and square it, it's positive. So you lose that sign information, which can lead to some false solutions. Let's see how that happens here. So if we see, right, we know, looking at this graph from Desmos, that there is only one real solution. The only real solution should be 3. But when we solve this using the techniques we know, so we square both sides, we have x plus 13 is equal to, this will be x plus 1 times x plus 1. This will be equal to x squared plus 2x plus 1, x squared plus 2x plus 1. This is going to be an algebra 2 equation solve, but it's going to lead us to a false solution. So we're going to have 0 is equal to x squared plus x minus 12. 0 is equal to, this is going to have to be a plus 4 times a minus 3, x plus 4 times x minus 3. And so we would see our solutions are x equals 3 or x equals negative 4. And let's do the one we know works first. If we check 3, we would have the square root of 3 plus 13 is 16 is equal to 3 plus 1. The square root of 16 is equal to 4. That checks out. But if we go to check -4, check -4, we'd have the square root of -4 plus 13 is equal to -4 plus 1. And so what we'd have here is the square root of 9 is equal to -3, which is not true. When you take the square root of something, it is only the positive version. But see, along the way, we squared both sides, right? This is a really interesting point here. Notice, if you squared both of these sides, it is a true statement. 9, the square root of 9 squared is 9, -3 squared is 9. But when you take a square root, it means only the positive version. So this is actually not a true statement. This is not a true statement. The square root of 9, it is implied that this just means 3. It does not also mean -3. So the only correct answer here is positive 3. 3 is the only answer that works here. -4 was a false solution.